Hi, and today we can discuss about the control theory. To control something, we have to require some control signal, and we can have a control signal of proportional nature, integral nature, or derivative nature. So, depending upon that, we have three type of controllers: proportional controller, integral controller, and derivative controller. So in control system, we design controllers depending upon our requirements. Sometimes we need a proportional controller alone. Sometimes we need a integral controller alone, and sometimes we may require uh, PID also. That is the designer's choice. A normal control system consists of a plant. Plant means suppose you want to control the temperature of a water in a tank. So the water in the tank is the plant. The controller is designed based on the mathematical model of the plant. That is, there will be a mathematical model for this plant. That is, there will be a mathematical nature, and that is known as transfer function in the case of a control system. The mathematical model is known as the transfer function of the system. The plant parameters change. That is, the water in the tank, the quantity can change, the density can change, all these things can change. So the performance of the plant may change. And now we can study in detail about proportional control. What is proportional control? Proportional control is the simplest of feedback control, where control action is proportional to the error between the desired value and the actual value of the system. That is, the controller action, that is, suppose the water in the tank will have a temperature of 30 degree, and we may require the temperature to be 35 degree. So there is an error. So depending upon that error, there will be a control action is generated. In other words, the bigger the error, that is, for example, if the error is, if the water in the tank has got temperature of 25 degree, and we may require the temperature of 35 degree, there is 10. So the error, bigger the error, the stronger the controller action. And this is the block diagram of a proportional controller system. So this is the process means the plant. So this g of s is known as the transfer function. G of s is known as the transfer function of the plant. Everything will be represented by a block diagram in the case of a control system. So that is one of the method to represent the control system, a block diagram representation. And we can have mathematical representation. So this is the proportional controller. This is the controller, and this here we will get the error between R of s. R of s means the reference. Reference means we will have a set point, and this is the required output. So the set point and the output will have an error, and that will be feedback through a transfer function, and we will get an error. So if the bigger the error, that error into proportional constant. Kp stands for proportional gain, and bigger the error, the bigger the control action. This is constant. Kp is constant. We can have high or low value for Kp, that we can see later how to choose the Kp. And the basic definition of the control system, the signal u of t is calculated using, that is, the u of t means this value, the value here, the value u of t will be calculated using Kp into E of t. Kp, this you can see, Kp into E of t will be the u of t, where u of t is the control signal. That is, the u of t will come here, u of t will come here, u of t, control signal, that can be a voltage to a motor, or the voltage to a heater, that is if you want to heat the voltage temperature in a tank. Then E of t, that is reference minus y of t, that you can see here, r of t minus y of t, reference minus y of t is the E of t, error signal, and Kp is the proportional gain. This is the proportional gain, and it is a tuning parameter. That is how we have to choose this is a question. How we are choosing this Kp is a designer's choice. Then the intuition. Now let us say we are trying to maintain the temperature of the room at 25 degree. That I have told you previously, water in a tank. Now we are trying to maintain the room temperature at 25 degree. It is currently at 22 degree. There is 3 degree. So the controller increases the heater power proportional to the error. That is 3 degree is there. So 3 into the error is now 3. When it increases to 23 degree, the error will be 2. So if Kp is constant, the controller action will reduces. If 24, again the control action will reduces. So as the temperature goes closer to 25 degree, the error reduces, so does the power. So the system pushes hard when it is far from the target and eases up as it gets closer. Another example, let us say we want the motor speed to be at 1000 rpm, but it is only running at 800 rpm. The error is 200 rpm. If Kp is 0.5, control signal will have an amplitude of 0.5 into 200, that is 100. If the Kp is 1, suppose you are choosing Kp is 1, it suddenly reaches 2000 rpm, that is the error will be reduced. But if the Kp, if you are increasing the Kp, there will be an overshoot. Sometimes it may not be at 100 rpm, it may increases to more than 100 rpm, it may reach 1100 instead of 100. So if you are using it in a bike, the bike may hit in the hit in another vehicle or may cause an accident. So the controller signal sends a signal of 100 units volts torque to increase the speed. Again, now we can see what is the transfer function. In control theory, transfer functions are commonly used to characterize the input-output relationship of the components or system that can be described by linear time invariant systems called as transfer function. Transfer function of a linear time invariant differential equation system is defined as the ratio of the Laplace transform. This is a mathematical term, and you might have studied Laplace transform. Laplace transform of the output response function to the Laplace transform of the input response function. That is, output response function means this one. Laplace transform of this to Laplace transform of this. So that is the transfer function. Consider this this is an open loop system G of s, and here there is no feedback, so it is an open loop system. So C of s is the output and R of s is the input. So the transfer function of an open loop system is G of s is equal to C of s by R of s. And transfer function of a closed loop system, so G of s, C of s, R of s. So R of s is the input and C of s is the output. So the transfer function here is C of s by R of s is G of s by 1 plus or minus G of s into H of s. That is, this may increase the error or decrease the error depending upon the error is positive or negative. So this is R of s is the reference input, C of s is the controlled signal, controlled output, sorry, C of s is the controlled output, E of s is the actuating or error signal. E of s is the actuating or error signal. And G of s is known as the forward path transfer function. G of s is forward path transfer function. H of s is the feedback path transfer function. And C of s is G of s into E of s. C of s is equal to G of s into E of s. And G of s into R of s equal to, that is G of s into R of s. It is if the error is 0, so the error is 0, G of s into R of s. So G of s into R of s is equal to plus G of s into C of s into H of s. So here C of s by R of s, finally you can come at a value G of s is equal to G of s, transfer function as C of s by R of s is equal to G of s by 1 plus G of s into H of s. This is known as the transfer function of a feedback system. Transfer function of a feedback system. I think you might have studied this in signals and systems, or we will study in detail in the control theory later, control system paper later. So this is the transfer function of a proportional control system. The plant is G of s 1 plus R of s, that is the transfer function. Proportional constant, that is C of s. Proportional gain, that is Kp. That is also but this is a output by input is a constant here, so it is Kp. Output by input is constant means it is a gain. It will have gain similar to the gain of an amplifier. So here we can use an amplifier, that is that amplifier is the operational amplifier with a particular gain. It can be negative feedback amplifier or a positive feedback inverting or non-inverting amplifier. The closed loop transfer function becomes Kp into G of s by 1 plus Kp into G of s. So this is the transfer function of a closed loop proportional control system. So here Kp will come here. So if Kp higher, the response will be higher. That is, it will have more sensitive to noise and overshoot. That is, I have told you previously, the motor speed may be higher than 1000. If you are setting to 1000, because of overshoot, it may reach 1100 RPM. Then the characteristics of the proportional controller. So the feature, the speed of response will be higher with the higher Kp. That is, previously we have seen here we have seen we are setting the RPM at 1000. If Kp is lower, the change is only 100 RPM. But if Kp will be higher, it may reach to 1000, or sometimes it may overshoot to more than 1000. So speed of response faster with higher Kp. So it is a designer's choice which value to choose for our design. Then the steady stater. So that is always there will be a steady stater. In the proportional controller, there cannot be 0 at all. That is, if there is 0, what will happen here? If there is 0 here, if there is 0, 0 into gain is 0. So there will not be any controller action. So always there should be an error for a proportional controller to work. If the error is 0, proportional controller will fail to work. So that is the problem with proportional controller. The main problem with proportional controller is we cannot reduce the error. Always there will be an error. The error will be not 0. And stability can become unstable if Kp is too high. Stability can become unstable. That is, there may be unstable overshoot more likely with high Kp, that I have told you. Then noise sensitivity increases with Kp sensitivity, that is Kp is higher, even if a small noise will pick up with this high gain. Then steady state error in proportional control. One of the biggest limitations of proportional controller is that it cannot eliminate steady state error in most systems. That is, we have discussed that we cannot reduce the steady state error in a proportional controller. Why? Because as the error decreases, the controller effect decreases. As the error decreases, the control effort decreases. That is, error is less, Kp into error will be, that value will be reduces. So at the steady state, the system might settle at a point where small non-zero error is equal to maintain the output. So always there will be an error. That means if you are using a proportional control to maintain the room temperature at 25 degree, it will never reaches 25 degree. It will never reaches 25. It will be always lesser than 25 degree if the Kp is small. If Kp is small, but if Kp is high, what will happen? It will overshoot to more than 25. Then it will come lesser to 25. That is, it will come below 25. That is, it will come below 25. So here our graph will go like this. There will be it will not settle. So what is the solution? We have to use integral control or PID controllers to eliminate the steady state error. But the advantage, now we can see the advantage and the disadvantage of proportional controller. So proportional controller is very simple to implement. That is, we can implement with a proper very simple gain. We have to put Kp. That means that Kp can be the gain of your operational amplifier. That is, gain can be set by inverting amplifier or non-inverting amplifier, or if you are using it in digital system, you can simply put a value for this Kp in your computer. And a quick response to error, the error can be reduced, requires minimal tuning. That is, we have to we have to tune only one parameter. But if it has got Kp, Ki and Kd, what is the problem is, if you are initially tuning Kp, then Ki, what will happen? Again we have to tune the Kp. So that problem will be there. That is, once you tune Kp, then you are tuning Ki, again there will be a disturbance in the Kp. So tuning will be difficult. And the disadvantage of proportional controller is steady state error, can cause overshoot and oscillations, not suitable for system with non-linearities or delays. Then we can see some of the applications of proportional controller: thermostat, controlling heater or cooler power; fan speed control; speed governors in engines. That is, you might have heard about speed governors in buses and lorries. So that in that case, what is happening is, we will cut the fuel to the engine after a particular speed. So the speed not cutting, actually we will not allow fuel more than a particular value, so that even if the driver presses his accelerator, the vehicle may not goes above a particular speed. Then level control in tanks. Then how we can tune the Kp? I have told you, we have to put a value for Kp. So here, if you are using an operational amplifier for tuning, we have to change the value of feedback resistor to change the gain. But if you are using a digital controller, we have to change only the value of the Kp. So start with a small value, gradually increase until the system responds quickly but without excessive or overshoot or instability. So this is the method. And tools like, there is a tool known as Ziegler-Nicholas tuning to tune the proportional controller, and this is a tuning method to tune or to find out the value of Kp, Ki and Kd. And we can have a summary. The control law, that is U of t is equal to Kp into E of t, that is the control signal is equal to proportional gain into error. Parameter to tune, we have to tune only proportional gain. Eliminates error, it will not eliminate error, there will be a steady state error. Complexity low, that is an advantage here. It will not reduce the error. Usefulness, limited to simple systems or as part of PID. Simple system, or we can use it as a part of PID. If we are using PID, that will be good. Okay, thank you.